So if you're having any trouble, I'm not responsible. Yeah.
That I volunteer.
So you should talk to them, okay? If you have, really, but if you do have any issues, let me know and I'll talk to Venki. You talk to Venki directly. And he's supposed to have assigned two of his students as assistants to help you. Who are they? Are they here? So yeah, let everyone see your faces, okay? So if there are any issues, these are the two people you talk to. All right? Yeah, really honestly. So, and they'll have solutions for everything, including your research problems. All right. Okay. I'll introduce you then. Okay. So it is my great pleasure to have Professor Jan Bowman give a series of 4 lectures on generalized radon transform. Professor Bowman comes from royalty in a sense that his advisor was Lars Hormander. So you can see he's got he descends from royalty. And he's actually a world expert in generalized radon transform. He also likes Indian cooking. I know for a fact, he's told me he buys Indian spices. He's also vegetarian. He buys Indian spices, cooks Indian food at home. All right. So
but here it's much better.
All right. Okay. And so it's a great pleasure to have Professor Bowman speak on generalized radon transform.
Okay. Thank you very much, and thank you very much for this generous invitation. And it's a great adventure for me and a great pleasure to come to India. This is the first time here. I actually, more precisely, the theme of my talk will be Radon transforms and wavefronts. The singularities. My focus will be on singularities in context of the Radon transform and tomography. The wavefront set is useful in connection with tomography, partly because of it helps to explain how boundaries and other contours are shown in the image, and also the analytic wavefront set, which I will talk about later, is useful for proving uniqueness theorems. But first of all, of course, the wavefront set has been extremely important the last 40 years or so in the development of partial differential equations. So this notion has a great importance for itself. So let's go to the singularities. Well, the purpose today, I plan to write down a brief sketch of the plan of the 4 talks. Today, first I will define the wavefront set. I will not assume that you know the definition, so I will take it from the beginning. And then I will talk about the relationship. Let me just indicate it like this. Here, R stands for Radon transform. So relationship between the wavefront set of the Radon transform F and the wavefront set of F is very interesting. And this relationship is also a special case of something much more general. And then then I will study more general linear operators, which I shall denote by K. And one can say much less for more or less arbitrary linear operators, but one can give an inclusion, which also has some, is quite interesting. And finally, then I will talk a little about weighted Radon transforms, and finally I have to say, talk a little about the analytic wavefronts. So this is a plan. But today it will be very, very elementary in some sense. Now, the purpose of the wave set is, as I said, is to describe singularities. What are we are interested in the type of singularity that I suggest to think of is jump discontinuities, and which could be the boundary of some object or some other. So, for instance, a jump discontinuity like that. And the purpose of the wave concept is to distinguish between the direction of that boundary. And we do this with Fourier transforms. So, yeah, this is anything else. So, you need to, what you need to know is that a compactly supported function or distribution is C infinity if and only if it Fourier transform decays rapidly, very rapidly. But I forgot to say something. We are not going to distinguish between the strengths of the singularities. So for a one variable function, a jump discontinuity and a jump of the function itself, or jump discontinuity of the first derivative, or even something much wilder, a delta distribution, we're not going to distinguish between those. So even a jump discontinuity of the 10th derivative would be considered a singularity here. So therefore, everything which is not C infinity would be singularity. So here is my first, as a starting point before I give the definition, I write down the following. As a proposition. A function or distribution f is in Rn is C infinity in some neighborhood of the point x0 if and only if there exists a C infinity function with compact support phi, which is different from 0 at that point, such that the product, Fourier transform of the product, decays very rapidly. For every n. So let's just, since this is so basic, in the definition which will come in a moment, let's just check this. Let's call this statement on the first line 1 and this 2. So assume first 1. It's a distribution, but here is x0, and we assume that it is C infinity in some neighborhood, take this here neighborhood. Then we can choose the C infinity function so that it also is supported in this neighborhood and different from 0 here. And then that product will be C infinity everywhere, and so it will be decaying rapidly like that. And conversely, if we assume this 2, then we know by the fact that I stated earlier that this product is in C infinity function, and since the phi function is different from 0 at that point, then f itself can be expressed this way, and phi is different from 0 in some neighborhood. So in some smaller neighborhood, f will be C infinity. So now comes the definition. I write it slightly informally, you will understand what I mean. Xc is, by definition, not in the wavefront segment. F can be a distribution, or you can think of function if you like. If and only if. So there exists a smooth function, compactly supported, and I want like that. Again, different from 0 at that point. Such that something similar to what I had here, but we want to restrict for, okay, I forgot. And an open cone. Open cone containing that zero vector in its interior. So I need to write
Oxide gum, not crazy. Not only so.
Thanks. 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 So I want to think of C0 as a little vector. And here's so the only difference is that I restrict the direction in which C has to fit. Nothing is forgotten.
You want to write open cone?
Open cone, thank you. Thank you. Thank you. So you need to see one example of how the definition works. In the plane, I choose F with a jump discontinuity. Like that. And then say that this is the x1 axis. So then I claim that the wavefront set of F consists of all points x1 for the points. Of course, it's smooth outside the jump, all such points, and C's which are perpendicular. I want to use a different kind. Only such C vectors. So I want to show you how the definition works. I want to verify that if C0 is not in that direction, but like this. Then this pair is not in the wavefront set. Of course, this is only non-trivial if x0 is on that jump line. But how do we verify this? Well, we are free to choose phi as we like. So I want to choose it as a product of a function of x1 and a function of x2. And of course, non-zero in the corresponding point. Then phi f hat is phi f one had. So f doesn't depend on x1. So therefore, this Fourier transform can be factored like this. Now this factor is just a smooth function, it decays fast. And this is certainly bound. And this decays fast. So this means that we have to choose gamma. If we choose gamma so that C1 necessarily tends to 0, kill my C0, I choose gamma so that and it must be a neighborhood of C0. But it's of course possible so that C1 necessarily tends to infinity as C tends to infinity with C in gamma. Then this, as I showed, this absolute value tends to 0 fast, as in the definition. So, but on the other hand, if we allow C to tend to infinity exactly in the C2 direction, this factor will, because of the jump, if C2 is different from 0 to 0, we will have to jump. So with a little, I'll come back to this. At least we understand that these directions are not in the wavefront set. Now we need to have a couple of tools. The first one, it's better to write on the, maybe this is so easy. Everybody remembers. So write an important number here. If C is in C infinity, then wavefront set of CF is contained in wavefront set. It would be strange if this would not be true. That is, if we multiply our distribution with a smooth factor, nothing new can come up in the wavefront set. This is more than a lemma. This is a theorem, or at least a proposition. Now comes the main step in the proof of this, which is a lemma. And I want to show you this lemma in detail because many proofs later on in the theory contain essentially the same, contain variations of the same argument. It says the following. I hope you don't mind if I use the terms D prime for distribution and E prime for compactly supported distribution. Very good. Okay. If somebody is uncertain, you can think of an L1 fraction compactly. Let F in E prime are M and Q F has the Fourier transform decays rapidly in subcode like that. So C C in some open code for every n. Let C is infinite. Then, well, and let I like to use this notation. It's a smaller cone, but so this is gamma, and this is gamma 0. The conic closure, which is actually the closure in the complement of the order, must be contained. That's what I mean by closure of that must be contained. But we always forget about the order. Then this product decays fast, at least. In the smaller code. So maybe the lower boards are more or less useless. Perhaps I can write one formula on this. Please tell me if I write something wrong or if something mysterious. So the Fourier transform of the product is a convolution of the Fourier transform. And then, in a way which we will have to do 3 dozen times, if I were to go through the whole theory, we split this integral into eta that are small relative to C and the other eta. For an epsilon that I'm going to choose in a second, maybe I can draw these figures here. I choose I think I can continue here. Choose epsilon so that eta less than epsilon value C and C in the smaller code implies C minus eta in the bigger code. That is certainly possible, and epsilon depends on the shape here. So if I have a large C here, then the radius of the little ball here is epsilon times absolute value of C. Oh, it should be a little larger. It should be like that. So it's a simple geometry that you can choose such an epsilon. Then, I don't plan to write anymore now. Because, for simplicity, assume now that f is in L1. Then the Fourier transform is bounded, and the Fourier transform C was also bounded. So then, well, regardless of whether f is in L1, the first term we know that this decays rapidly by the assumption about this factor and that factor is bounded. So therefore, this will be decay fast as sequence. But for that factor, it's a slight simplification to assume that f is in L1, which makes f hat bounded. Then I take out the constant for f hat, and I get just, I have to integrate the absolute value of c hat all side of all like that. And since c is infinity, c hat decays rapidly, then also the integral outside for decays. So certainly both these things will be for every m. That's not exactly the same m here, but we know this for all m. So what next? Maybe one can write, no, not really. I think the next thing to do is to yeah, of course. There are two very important things. I forgot to say. I think the lower boards are not very useful. But this example. First of all, obvious fact that VFF is harmonic in C value. This is absolutely obvious, and by this I mean that XC is in a wave-front set if and only if as long as lambda is a positive real number. That is the size of the C vector.
Not in the wave-front set.
Yes.
On the other side.
Yes, I wanted this. Thank you. Very good. Only the direction. This is obvious from the definition. We can come back to what happens for negative lambda here. But first I want to state that let me denote by pi, well, the Rn sometimes denoted by capital X, the X space. Pi X is the projection where you simply forget the C value. Oh, well, I see some people writing. I should say that I did, since I realized that there's a lot of material that I hope to tell about, and there will be some technicalities. I wrote some lecture notes, which have, it's about 20 pages. Containing not everything I talked about, but a fair amount. And half of this should be made available today on the website of the Institute. There may be errors there, because I wrote them rather recently, so it's helpful if you point out what is not correct. Yeah, but anyway, this is a projection, and the statement is that the projection of the wavefront set of F is equal to the singular support. And this is defined as the complement of the largest open set where it is smooth. So exactly, it's a set of singularities in the sense that I explained earlier. Recall that the union of all open sets in which the restriction of F is smooth is also an open set. That is the largest open set. So the complement is a closed set. That is simple. And how do we know this? Well, one inclusion is obvious, and the other requires this proposition. Oh, well, I forgot to say that the proposition is an inequal consequence of whatever. Which inclusion is obvious? It is that if x 0 is not in the singular support, then the function is smooth in a whole neighborhood, and so there is obviously no C at all in the wavefront set. What does that mean? It means this, I think, because of complement. But how do we prove the other, this? Well, then we have to prove that if a certain point, x0, is not in this projection, then it is not in the singular support. But what does it mean that it is not in the projection? It means that for every C direction on, say, the unit ball, x0 C is not in the wavefront set. For every C on the unit ball. So we get, for every C, we get such an open code with different fees. And by the Heidelberg lemma, yeah, thank you. Actually, you're very important. Thank you. So by the Heidelberg, we have a finite number of such poems that cover the complement of the origin. And phi f hat decays fast, but there's a problem. We've got different fees. So, but now we are free to choose the product of all those fees. They are all different from 0 at the point, and then we need the lemma. So it's a small point. You can think it to yourself. So that's okay. We need the next to be able to understand how the wavefront set behaves under variable measures. Before I do that, the definition itself is interesting. So even before you go into the theory, you can directly from the definition you can entertain yourself with a number of examples. For instance, such an example, a corner like that in 2 variables. We know already that all co-normals. I say co-normals, not normals. I will come back to that because the C is actually an element of the cotangent space. I'll come back to this. But what happens at this point? The truth is that all C vectors above that corner point. And another example one can do it's directly with a little f, and it's you learn from it, is a characteristic function of disk. But we should get, in a couple of minutes, we'll get theory that answers the question. So, what happens if we make variable transformations to the wave set? But the translation is trivial. So let's you first think about affine transformations, and then again, translation is trivial. So consider a linear map from R to Z. I will call this y, this y, and this x, and here is a, and this is f. So f tilde y is equal to f x. Then I just make a short computation. We imagine that we have already cut off f with a smooth function as in the definition. We take the Fourier transform and just want to see what happens when we change variables like that. So then f tilde at eta is interval into minus y eta f a y is y. Do I write order now? I hope so. Then I want to bring in x, so I get e to the minus a to the minus 1 x eta f x dx, but there is a constant which makes no difference at all. Minus 1. And now here, what is interesting happens up here. A minus 1 x dot a. And let me write inner product instead. Same thing. It's the same as x a minus 1 star, but that's the same as a star minus 1 x. So this is a C vector that will come up. So therefore, this is this constant, which you get e to the minus I x. Let me write C. F x x. So the thing to keep track of is the relationship between the x and y points, which is trivial, and the c and eta. So my claim is that, of course, I can't do every detail. My claim is that x c is a f from f is equivalent to y eta in tilde if, first of all, obviously A maps that includes 0. Obviously, A must map oops, I did something wrong here. X equal to, it's very easy. AY. Yeah, so this is good. And no, is it done?
I don't know. Yeah. A y 0 is at 0. A y 0. A is from y to x.
Yes, that's right. That's right. That's right. And we had it here. So A star minus 1, A plus 0 is C0, so obviously, yeah, should be the other way around. So, but I would like you to think of this geometrically. It's very easy to make this kind of mistake I did, so I want to look at my So if my goal is to explain geometrically, clarify why this relationship. So if this is a y space here, and this is the x space, and here is that point, and that is a plane which I call hyperplane for n here, and here is L tilde, and the little tangent vector is actually a tangent. These are vectors in the tangent space at the point, which is isomorphic to R itself. So L tilde consists of all A, B, such that B is in L. Now, if eta 0 is perpendicular, conormal to L, that means, it means that eta 0, V is 0 for all V in L, but eta is A star C0. Which is the same as C0 A V. So see that this means that C0 is perpendicular to L0. So, my students want at first to think of the C vectors as vectors in the X space itself, but this is a very misleading intuition. They are elements of a dual to the tangent space, dual space. So actually, geometrically, they specify a hyperplane in the X space, or actually the tangent space to the X space. So whenever needed, one should shift the intuition and think of these C vectors as specifying a hyperplane in the tangent space to the point. Now, I'm not much time left, but so I have to completely skip the need to know, perhaps not completely, I want to say, we need, of course, do the same thing, non-linear. That means that I have a few minutes. So this was I wrote this down in the notes. So now we have this y, and we have instead this diffeomorphism. And we want to understand what it does to the wavefront set. And we try to do something similar. I write down the result. It is completely analogous. It says, well, perhaps I can save writing. Yeah, I can. F tilde y is F C y now. This is the diffeomorphism. So corresponding to this, we have of course x0 equal to y, y0. Must be corresponding points. And corresponding to the other statement, we get h comma 0 equal to psi prime y0 star c0. What does this notation mean? Well, psi prime at the point is a linear map. It's a differential of c at the point. And we have to take the adjoint of that linear map in the same way as before. So, one word, just one word about the proof. Since we had, one wants to do the same thing as I did here, but then from the start, one can, we know the corresponding statement for linear maps, non-singular. So therefore we can make assume that x0 and y0 are the origin, and also we can assume that the differential is the identity. at the point. This means that psi y is equal to y plus. So one uses this assumption and is able to prove. Assuming that f has no wavefront in a certain direction at the origin, the same is true of f tilde. By actually a variation of the argument in that first level. Now, the result of this is that we know now, for instance, for the characteristic function of the disk or a ball, that the wavefront set obviously singular support is the boundary. The question is only what c directions are in the wavefront set. And it can only be the conormals. Why is that so? Because the problem is completely local one, so it's enough to consider study a little neighborhood like that, and in such a neighborhood we can make a diffeomorphism so we can straighten out the boundary, so it becomes, for instance, the x1 axis. And then it's an exercise, a useful exercise to interpret this statement that I wrote down here. That it gives exactly what we need, like that. Now I spoke without, I like to be interrupted with questions, but I have spoken without pause, so I haven't given you a chance. I'm sorry about that. But please. There are two useful problems more that I would have planned to tell you. I have only time for one. I will save the next. So let me choose restriction to submanifold. The other was integration to submanifold. It's very interesting. So wavefront set helps us to do things with distributions that used to be forbidden for many decades. And one is to take restriction to submanifold. Observe that already for an L1 function we have this problem. Because if f x1 x2 is equal to h x2 with h in L1 form, it does not make sense to take restriction to the submanifold x equal to k, say. I mean, here we have this nice function in the plane, and I want to speak about its restriction to such a line. It doesn't make sense because it is as impossible as talking about values at particular points of the level one function. On the other hand, if our function is like that, it works fine. Because then the restriction will be fx equal to h x1 minus k. Translation of the L1 function. So, and for distributions, there is the situation that in some cases it's possible, in some not. For instance, if fx is x1, x2 is equal to the delta x1 minus x2. This is a measure with a constant density on the diagonal. It makes sense to take restrictions. So the answer, the general fact, is that very nice. Let's see how yeah. This is how I wanted to. Let f to be prime or and assume x prim 0, 0, c is not my transit f for all x prime.
X prime is everything up to n minus 1.
For all, yeah. Of course. X is equal to the factor. This is by notation. This I'm considering the submanifold Xn equal to 0. And geometrically, what I'm assuming is that for all conormals, I'm going to use the geometric formulation of this, that S be this submanifold, this plane, hyperplane, n star S, I will often use, that is the conormal manifold. It consists of all xc, such that x is in S, x is in S, and c is conormal to S at x. So in coordinates, this is, of course, c and different from c. All these are forbidden. I should better, sometimes I write this way. I write this green here, and then I look for red. And these are forbidden. So why is this true? I have 1 minute. To define the distribution. Well, obviously we only need to do it locally, so we can cut off f by multiplying by a smooth function, so we can assume that it is compact support. And then I write the action of this distribution. I claim. Let me write this one. Integral f. I need just one form. 0 to x prime dx prime. I don't need to write anymore. I just want to explain why this. First, why two things: why it gives what we want, and why it makes sense. First, if f is an, say, continuous compactly supported function, why is this what we want? Well, the integral of the partial Fourier transform with respect to xn that is, in this case, f0, f x prime 0. Because integral over one variable Fourier transform is equal to the value at 0 of the function. But now, then I've used the fact also that the generalized Schwartz formula in the x prime variables. I take it also the Fourier transform with respect to x prime and multiplied by that Fourier transform with the minus sign is the same as this integral. So this is the correct formula for continuous functions with compact support. And why does it make sense for distributions under this assumption? Well, because I have already cut off f. Because of the wavefront assumption, this thing decays fast in this code, in such a code. And this thing decays fast in that direction. So if capital value of c is large, then certainly either c prime is large, then we are out here and that is small. Or Cn absolute value is large compared to C, and then we are in that code. So this is also compact. So that's okay, 1 minute over time. So, well, that's all I have to say today.
So thank you, and so Professor Bowman will continue with his lectures tomorrow. So we meet in half an hour.